In this video, we're going to talk about iterated integrals. An iterated integral is two integrals of a function of two variables. The inside integral here is with respect to y. The outside integral here is with respect to x, or vice versa. Over here, the inside integral is with respect to x. Outside integral is with respect to y. When we compute an iterated integral, we always work inside out. So for the first one, looking at the left one, like I mentioned, it's the inside integral is with respect to y. So we would integrate with respect to y, doing kind of a partial integration, if you will. We're going to treat x like it's a constant. This leaves us with a function of x when we're done, because we're not going to replace anything with x. Everything here is done in terms of y. Call it capital F of x, and then we do the regular old definite integral for f of x. So let's look at a specific example here. We have the function 2xy plus 3x squared y squared dy dx. So the y is going to go from 2 to 6. The x's are going to go from -2 to 1. So again, we'll work inside out. An antiderivative here for 2y would be y squared. So we get xy squared. Antiderivative for 3y squared would be y cubed. So we get x squared y cubed. Plug in your endpoints. For the y's, notice we still have the x's. That simplifies to the integral from -2 to 1 of 208 x squared plus 32x dx. Find antiderivatives for those. That's just a polynomial, so that's pretty straightforward. Plug in your endpoints and get 576 in this case. In the previous section, we talked about doing double integrals over rectangles and had the double limit of a double Riemann sum definition. Well, we have a theorem that's actually referred to as Fubini's theorem that allows us to calculate double integrals by using iterated integrals. And what it says is that if you have a continuous integrand over the rectangle, then you can just calculate the double integral by doing the iterated integral. And the order doesn't matter. You can go dy first and then dx, or dx first and then dy. So let's do an example here where we're going to use Fubini's theorem to evaluate the double integral. So let's say we have the double integral of x cosine xy, and we're going to integrate that over the rectangle 0 to pi over 2 cross 0 to 2. Now, again, according to Fubini's theorem, it doesn't matter what order we do this in. Okay? We can integrate with respect to either variable first when we're looking over a rectangle. However, if I try to integrate with respect to x first, we would have to use integration by parts. So I think I'm going to skip that for the time being, and let's integrate with respect to y first instead. If we integrate with respect to y first, then we have the integral from 0 to pi over 2 on the outside, integral from 0 to 2 on the inside, dy dx. This now becomes basically a u substitution. You could let u equal xy, then du would be x dy, so it's antiderivative then. We're just going to get a sine of xy, evaluated from 0 to 2. Plug those values in, you just get sine of 2x, which is a lot easier to integrate with respect to x now. Get -1/2 cosine 2x, your limits go from 0 to pi over 2, and if you plug those things in, you'll get 1. All right, let's do another one here. Let's say we have the double integral over a rectangle of e to the x over y dA. Our rectangle is 0 to log 3 for the x's and 1 to e squared for the y's. All right, so first thing, whether I integrate with respect to x or with respect to y first doesn't really matter here, because both of those are fairly easy to integrate with respect to in this case. So we'll just set it up as dy dx. But notice here in this case that we've got y's that don't matter, we have x's that don't matter when we're integrating with respect to y. So in particular, I could take this e to the x and I could pull it in front of this integral. Because as far as this integral is concerned, x is a constant, so I can pull it out in front. So now I have a definite integral of 1 over y dy. Whatever this simplifies to is kind of irrelevant for the time being. This is a number when we're done, right? So I can pull it outside of this integral. So now we have a product of two integrals. So the point of this is that if you've got a function of two variables that can be separated into a product with just x's and just y's, so this would be e to the x times 1 over y, just x's and just y's, and your region is a rectangle. That's important as well. Your region has to be a rectangle, like we have here. Then you can actually split your iterated integral into two separate definite integrals and just multiply them together. Now again, we cannot have variables in our limits of integration here to be able to do that. Remember, the whole reason why I was able to pull this thing in parentheses outside of this integral is because we said this is a constant when we're done. Well, if you had a variable in here, that variable would be an x variable. I wouldn't be able to pull it out in front because when it's inside the integral, it says we have to integrate it. Okay? But regardless, now we can do these in individual pieces and then plug in your endpoints and evaluate, and it should get 4 in that case.